Hey everyone. So today we're going to be taking a look at section 4.1 and 4.2, which will go over the constant e and the derivative of exponential and logarithmic functions. So the first thing that we want to talk about is the number e. So we've got two different ways to represent the number e, but they're going to give us the same thing. The first is that e is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power, or e is equal to the limit as s approaches 0 of 1 plus s to the 1 over s power. Now both of these limits will converge to e equals 2.718281828 and so on. E is an irrational number, meaning we can't represent it by a fraction. The decimal will never end, and it also never repeats. So it's similar to pi in that sense. Something important to remember is that e is just a number. So if I were to try to take the derivative of e, I would get 0 because it is a constant. If we want to test to really see how we're getting these values, you can kind of just manually compute these limits. So if I want to take the limit as something approaches 0, well, I can start at negative 0.5, negative 0.2, negative 0.1, negative 0.001. And then I can also do it from the positive end with 0.5, 0.2, 0.1, 0.01. And as you can see right here, we are converging to this number e. So what would be the derivative of e to the x? Now we know that e is just a number, but e to the x is an exponential function, so we should be able to take its derivative. Now they say that in order to take this derivative, we need to accept that the limit as h approaches 0 of e to the h minus 1 over h is 0. And if you were trying to plug in 0 right away, we would get e to the 0 minus 1 over 0. This would be 1 minus 1 over 0, which is a 0 over 0, and that's an indeterminate form. So they say just believe this, that this limit will be 1, and then we should be able to use the four-step process to find the derivative of e to the x. Now later in calculus, so sometime in the next chapter, we'd actually be able to prove this is true. We're going to use something called L'Hopital's rule to show that, but that's for another chapter. So let's start with our four-step process. So we're going to do f of x plus h, and that would be e to the x plus h. So step 2 is we're going to take f of x plus h minus f of x, and that's e to the x plus h minus e to the x. Now here we can actually do some reduction. I mean, it won't do much until our next step, but I can factor out an e to the x. And then what I'm left with is e to the h minus 1. So that doesn't help us too much right now, but let's go ahead to step 3. So step 3, we're going to take f of x plus h minus f of x all over h, which is going to be e to the x times e to the h minus 1 all over h. And then in our fourth step, we're going to take the limit as h approaches 0. But before I do that, I'm going to just say I can pull this e to the x out. This e to the x can come outside of the fraction, and I'll get e to the h minus 1 over h. And now for step 4, I'm going to take the limit. So this is the limit as h approaches 0 of f of x plus h minus f of x all over h. So this will be the limit as h approaches 0 of e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now we know that this here is 1, meaning we're left with just the limit as h approaches 0 of e to the x, which is e to the x. So the derivative of e to the x is e to the x. So in our last slide, we said that the derivative of e to the x is e to the x. So dx of e to the x is e to the x. So that's just something that we're going to memorize. The derivative of e to the x is e to the x. And now let's do a few examples with that. So let's take the derivative of 5e to the x minus 3x to the fourth plus 9x plus 16. Well, the derivative of 5e to the x is going to be 5e to the x. And then all the other terms, we know how to use using the power rule. So minus 3x to the fourth, well, that 4 is going to come down, so we're going to get 12x cubed. Derivative of 9x is 9, and the derivative of 16 is 0. So this would be my final answer. Now in B, they're doing something a little tricky. So let's see. If we're going to take the derivative of negative 7x to the e, well, e is a number. Remember, even though it looks like a variable because we use a letter, it's a number. It's 2.7 something. So we're going to treat it just like a number in this case. So it would be negative 7e x to the e minus 1. That's power rule. The derivative of 2e to the x will be 2e to the x. And the derivative of e squared, well, remember, e is a constant, so e squared is also a constant, so that's going to be 0. So this is my final answer. Few more examples here to test taking derivatives with e in it. So for C, the derivative of 4e to the x is going to be 4e to the x. The derivative of 8x squared is going to be 16x. The derivative of 7x is 7. And the derivative of negative 14 is 0. So I'm not even going to worry about it. Now let's take the derivative of x to the 7. So that's going to be 7x to the 6th minus 5x to the 4th. The derivative of e cubed, again, e is just a constant here, so e cubed is going to be a constant. So that's going to be 0 minus the derivative of x, well, that's going to be 1, plus the derivative of e to the x, well, that's e to the x. On this slide, we're going to be talking about logarithmic functions. So remember, logarithmic functions have a lot to do with exponential functions. So just like we were dealing with e to the x, now we're going to start looking at the natural log, or log base e of x. So just a reminder that if we're looking at something like y equals the log base b of x, the domain is from 0 to infinity, and the range is from negative infinity to infinity, where if we were to look at an exponential like x equals b to the y, our domain is from negative infinity to infinity, and our range is from 0 to infinity. So the domain in our log, or our range in our log is the domain in our exponential, and the range in our exponential is the domain of our log. On this slide, we're going to be taking a look at y equals b to the x and log base, or y equals log base b to the x. And as you can see, they are symmetric with respect to the line y equals x. So if you were to flip the black function over that line, we would get that blue function exactly. So exponentials and logarithmic functions have a lot to do with each other. So another reminder about logarithmic functions. The two commonly used bases that we see will be base 10 and base e, which is also called the natural log. So if you see a log with no base written, we usually will just assume that that is the log base 10. And then ln is usually used for the natural log, or log base e. If you go into computer science, you might see one that's log base 2, which is usually referred to as LG. And I believe both letters are capital, but that's more for computer science. Now, the derivative of the natural log, they say that we're not going to show the proof here, mainly because it's a little above this class. but the derivative of ln of x is 1 over x. And this is just something that we're going to have to remember. So just like we've got the derivative of e to the x is e to the x, we can now say the derivative of ln x is 1 over x. Now let's take a look at a few examples. So they say for y prime, or find y prime. So if y equals 3e to the x plus 5 ln of x, well, that means that y prime, its derivative, is going to be 3e to the x plus 5 over x. You could also write that as like it's 5 times 1 over x. For the second one, we're looking at x to the fourth minus ln of x to the fourth. Well, now, not taking the derivative yet, this is really x to the fourth minus 4 ln of x. And that's just using the logarithmic property where you can drop the exponent down. So now to take its derivative, y prime, the derivative of x to the fourth is 4x to the third minus 4 times 1 over x. So this is 4x to the third minus 4 over x. And that would be our derivative for y prime. A couple more examples, just so we can keep taking a look at this. It says find y prime for y equals 10x cubed minus 100 ln x. Well, that means that y prime, this power rule, so we're going to get 30x squared minus 100 times 1 over x. So that's 30x squared minus 100 over x. Now in D, they're trying to be a little more complicated. So the first thing I'm going to do is I'm going to use this logarithmic property to move that 5 down. And then the other thing to take a look at is the ln of e squared. This is really 2 ln of e. And depending on how familiar you are with logarithms, the ln of e is 1. So this is really 2 times 1, which is 2. So if I were to rewrite this equation, I'm going to get 5 ln of x plus e to the x minus 2. And now I need to take the derivative. So y prime is going to be 5 over x plus e to the x. And the derivative of negative 2 is 0, so I don't even have to bother with that. So every once in a while, the logarithm will pop back up, and we just need to keep that in mind, because this is a constant. Even though it looks like it's a variable, e is a constant, so the natural log of a constant is still a constant, even if it's being squared. So on this slide, we're just going to be talking about the derivative of exponentials and logarithmic functions. So the two that we've covered are here on the left. We have covered e to the x and ln x. The derivative of e to the x is e to the x, and the derivative of ln x is 1 over x. And honestly, that's what we're going to use a lot. So you want to make sure to have that stuff in the red box memorized. Now, what if we're not using e? Let's say we're using some other number b. And they do tell us that b is positive and not equal to 1. So how would that change? Well, they do give us an equation for the derivative of b to the x. They say that it is b to the x times ln b. So this is tacked on at the end. And then they say, well, if it's log base b of x, we're going to get 1 over ln b times 1 over x. So this is added on. So the stuff in red, this is what we would expect. And the stuff in blue is what's additional because we're not using e to the x. So again, I mean, this stuff really isn't too bad. And I would say the stuff that's in blue does not come up very often, at least not in calculus. The stuff in red is what you're expected to know, just have it memorized and ready to go. So the stuff in blue, if you see a problem that's requiring you to use an exponential where it's not base e, or a logarithmic function where it's not base e, you might want to refer back to this slide. But honestly, the calculations aren't any harder. On this slide, that we're going to practice taking the derivative of exponentials and logarithmics that aren't using the base e. So for a, g prime of x, we need to take the derivative of 2 to the x. So that's going to be 2 to the x times the ln of 2 minus the derivative of 3 to the x, which is going to be 3 to the x times the ln of 3. For b, we're doing the same thing, but this time it's a logarithmic function. It's log base 4 of x to the 5. So I'm going to use the power rule for logarithms to take this 5 down. This is going to be log base 4 of x. And if I do that, when I take the derivative, g prime of x, this is going to be 5 times 1 over ln of 4 times 1 over x. So this will be 5 over ln of 4 times 1 over x. Slide 6, so just more of the same here. They want us to take the derivative, and we're going to have exponentials and logarithmics that aren't base e. So for the first one, g prime of x. X to the 10, well, that's just a normal power rule, so the 10 is going to come down, x to the 9. And then the derivative of 10 to the x is 10 to the x times ln of 10. For d, we've got log base 2 of x minus 6 log base 5 of x. So g prime of x is going to be 1 over the ln of 2 times 1 over x minus 6 over the ln of 5 times 1 over x. So some closing thoughts on this section. I know that we combined 4.1 and 4.2. The reason we did that is that e to the x and ln x go together so well that it's worth talking about them at the same time. And what you really want to get from this section is that the derivative of e to the x is e to the x, and the derivative of ln x is ln x. So as long as you can remember that, I would count this section as a win. And we'll see exponentials and logarithmics come up for like the rest of the year.